Dilating a figure on the coordinate plane. To dilate a figure, we need a center of dilation and we need a figure itself. To make things easier, I'm going to make the center of dilation the origin. That's going to let me use the coordinates and just multiplying the coordinates to get my dilated coordinates. So I'm going to start off with a segment. And it doesn't matter what quadrants we're in. Label this A. I'll label that B. And then I need to figure out their coordinates. And then to dilate, I would pick my scale factor and I would multiply each coordinate on each point by that scale factor. So to keep things small and on my paper, I'm just going to stick with a scale factor of 2. So this would become 4, 10. And this would become -4, +4. Notice that I included the prime marking, so I know that that's my image, not my pre-image. So there are some properties that we can observe. First thing that you might notice is the increased length. I could use the Pythagorean theorem to figure out the length of AB. And I can use the Pythagorean theorem again over here. And I can see that the coordinates were doubled and the lengths were doubled. That's one observation I can make. I can also see, more or less by looking at it, these two look to have a similar slope. They look to be parallel. And I can test that. Here I see that I have a slope of 3, 4. So the slope of AB is +3, +4. And the slope of A prime, B prime, I went up 6 over 8. And I can see that that's going to reduce to 3/4. And since the two slopes are the two slopes are equal, then I know the two lines are parallel, and I can add a parallel marking to the lines. So that's marked on my diagram. I could also look at some of the properties by drawing in some auxiliary lines. I'll use a different color for that. And I could verify parallel lines by measuring with a protractor and seeing that I have, looks like a right angle there. And a right angle there. So I would have corresponding congruent angles. I can also measure the distances of the segments formed on my auxiliary line. This distance here, which would come from taking 2 squared plus 2 squared and finding the square root. I could find this distance as well by taking the square root of 4 squared plus 4 squared. It's approximately 5.6. And I can compare the two, 2.8. If I multiply that by my scale factor, 2.8 times the scale factor, which is 2. should use the approximate size because I've been doing a lot of rounding here. And I can see that the distance from my A endpoint to the center of dilation and A prime to the center of dilation was in the same proportion as the scale factor. All of these properties will hold with polygons, with the additional property that all of the angles in the polygons will remain congruent from the pre-image to the image. Performing a dilation with GeoGebra. The list of tools we could use would be segment tool, polygon tool, point, creating a line, measuring angles, distance, and slope. I'm going to start off by creating a polygon since I dilated a segment in the graph paper video. And then I'm going to use the dilation tool, which is down here at the bottom. I select the object, select the center of dilation, and then I create my scale factor. And then I have a dilation. Let me just label that. Here's my center of dilation. First off, one of the basic things that we learned the first time we talked about dilations was that we should have same shape, different size. So overall, I can kind of get that impression. I could check this pretty quickly by using the angle measure tool. When you select angles in GeoGebra, go in a clockwise direction. So I know that I have the same shape and different size because all of the angles stayed the same and it increased in both directions, not just one. It wasn't a distortion, it was a true enlargement in this case. We can also verify some of our more intermediate properties, like seeing if all of the sides increase proportionally. And I can do that using this distance tool. This one's a little bit harder to see. You have to do a little bit of math to verify this. So I'll take a couple and I'll run them through the calculator and see whether or not that relationship held true. And I get 902, which is close enough. There must be some rounding. I could also try 2.71 times 2, and I get 5.42, and the rest should hold as well. So we can also verify the intermediate observation that all of the segments should be parallel. And the easiest way for me to do that is using the slope tool. I can see I created two slopes. Both of them are 0.47. Same again. And same again. I could also look at the advanced observation using an auxiliary line. So when we did this with a segment, we found out that the distance from the pre-image vertex to the center of dilation compared to the image vertex to the center of dilation increased proportionally with the scale factor. The line. You can see if I draw lines from the vertices of the image back to the center of dilation, the vertices of the pre-image also lie on the same line. That's another advanced observation. just created segments. You can't see them because they overlap with lines, but I created segments from each vertex back to the center of dilation. And I can see that I'm getting approximately double, meaning there's probably some rounding going on. And finally, because I can't resist making a meme, there you go.